Hi everyone. This talk presents the paper How to Pick Your Friends, a game-theoretic approach to peer-to-peer overlay construction. This is my joint work with Professor Aviv Zohar, and we're both from the Hebrew University. In this talk, I will first describe the isolation attack on peer-to-peer networks, an attack in which the attacker separates parts of the network by manipulating the way the peers choose their connections. We will first show how naive implementation of the peer-to-peer protocol may accelerate the attack. Then, we will present the game-theoretic approach that was discussed in the paper, modeling the interaction between the defender and the attacker as a game, where the attacker obtains different types of peers in different costs, and the defender should choose his connections out of the available peers. Later, we restrict the model to a limited buffer scenario, in which the peer gets a stream of available peers, but can remember only a subset among them. Isolation attack is a concept that was discussed broadly in the literature, in which a peer, or a group of peers, connect only to peers that are controlled by a single attacker. In this case, the attacker can distort the peer's view on the network. So, if the defender is the peers on the bottom right, and he is connecting to only attacker peers, then he is isolated from the network. Specifically, he can filter, delay, change, and damage the messages between the isolated groups and the rest of the network. As a teaser, Bitcoin itself employs countermeasures against these attacks. Simplifying the process a bit, Bitcoin uses buckets, which splits the list of known IP addresses by hash on their IP prefix. When a new node arrives, it calculates the hash of the IP/16 prefix and inserts it into the bucket. When a new node arrives to a full bucket, it will evict the oldest node in the bucket and store it against it. In this talk, we will formulate and improve this approach. Schematically speaking, each peer-to-peer system should establish a network protocol which answers two main questions: how to choose the peers to connect, either request peers to establish a connection or accept incoming requests, and how to continuously maintain the list of available peers under restricted memory. To give a small intuition, take the naive implementation as an example. The naive peer wants to create a fixed amount of connections. It first accepts every requested connection and then sends a request to establish new connections by uniformly selecting peers out of the peers that it knows. Moreover, the peer must choose an eviction policy, which names to choose which of the IPs in the buffer it should remove. The naive does it uniformly. There are many attack vectors to this naive approach. The first idea is that an attacker can create only a few peers and actively request connections from the victim as soon as it gets connected to the network. In this way, the attacker manipulates the policy of first accepting pending requests and only then establish connection by its own. Another attack is that the attacker can create many peers and propagate them over and over again. Because there is no validation on the true identity of the nodes in the network, the attacker can create and maliciously propagate his peers that they will ultimately evict all the other honest peers from the list of the victim. This will cause the victim to choose the attacker with very high probability. Moreover, without any method to recognize repropagation of the same peers, the attacker needs to create only a small number of peers, the size of the victim's buffer. Of course, there are more possible attacks on the naive strategy. In our paper, we are taking a game-theoretic approach to overcome isolation attack. On the basis of our approach, we assume that an attacker has cost to establish peers in the network. As an example, intuitively, it might be hard for the attacker to create a peer that is very close which means low ping RTT, to the defender. Another example, and this is our main example, is that it is hard for the attacker to create peers that have very different IPs. In particular, it costs less to create two peers with IP addresses that share the same /16 prefix, which are the first 16 bits, rather than create two pairs with different /16 prefixes. On the other hand, the defender wants to choose his connection in a way that will maximize the cost of an attack. This takes us to the Limitless-Buffer Game, which is a theoretic game where the defender knows all the pairs in the network and can choose any subset of pairs to connect. The strategies of the attacker are which pairs he should obtain out of the whole network. We assume that in a successful attack, there is a constant winning prize for the attacker, and we conclude a formula. Notice that with this formula, the pair needs to know all the other pairs in the network, which is not feasible in large networks. We will later see how we can remove this requirement. Highlighting few of our results in this game. The first is that in every Nash equilibrium, an attacker either does not corrupt any pair, which means it does not attack at all, or it spreads the probability of corruption over all the pairs, which means that it has a small probability to corrupt each one. The second result is that if corrupting one group costs more than another, then the defender will choose pairs from the first group with higher probability. The last result that we will show in this theoretic game is that we can handle missing knowledge, and the defender can err on the side of caution and overestimate the damage from an attack. In particular, a safety level in a game with overestimated damage is a safety level on the actual game. The final step is the buffered game, in which we take the theoretical approach into the real world. In this scenario, the pair has a limited buffer to store pairs from the network. We use two tools here. The first is Bloom filters, which allow us to recognize unique pairs, and thus the attacker cannot advertise his pairs over and over again until they will enter the buffer. The second is an equilibrium relation of the defender's strategy. The idea behind this equivalence is that the defender does not really need to know all the pairs in the network, but only recognize their class. The classes are formed such that each group is a good representative of the class in all the Nash equilibria. This leads us to a new game definition. In this game, the size of the strategy space of the defender is the number of equivalence classes. Thus, there are cases in which it is practical. Finally, our main theorem shows that the game value in both games is the same. Therefore, we retrieve the same security in the feasible game. Taking the theory into practice, we showed an algorithm that provides a buffer management protocol. This protocol, given a stream of pairs, chooses uniformly a representative from each equivalence class and store it in the buffer. We can use the example from the beginning of the talk. Here, the IP masks are the base of our cost function, and the equivalence classes are the masks. Intuitively, the algorithm works as follows. Given a new pair that needs to be stored in a full bucket, we will evict another pair only with probability that corresponds to the number of pairs that we saw on this same bucket. If we need to evict, then choose uniformly a pair from this bucket and replace it with the new. In the paper, we describe this algorithm in detail and prove that it preserves a uniformly selected representative of each class. Finally, we retrieve the following probability of successful attack as a function of the invested money by the attacker. As before, we assume that it costs less for an attacker to obtain two pairs with the same IP/16 prefix than with different prefixes. The left figure compares our strategy to the Naïve strategy that we discussed earlier, where the attacker just overrides the buffer of the victim by advertising his peers over and over again. The second benchmark uses Bloom filters, but selects uniformly from the buffer. Regarding the right figure, our model assumes that the attacker tries to isolate a single node. The next experiment showed that selfishly adopting this method provides strong protection for subsets of nodes as well. For example, if the attacker tries to isolate a set of 2 nodes, the attack becomes harder. The figure applies our selfish behavior to multiple peers and examines the probability of success for an attacker that tries to isolate all these peers from the rest of the network. To conclude, we presented the game theoretic approach to establish a practical protocol to manage peer selection and maintain the network's view. We first show an unrestricted scenario, in which the peer knows all the other peers in the network, and then showed a reduction to a smaller feasible case, in which the peer only stores an instance of every equivalence class. Finally, we show the impact of our approach on the Bitcoin network. Thank you. Please feel free to contact us for further questions via our mail.